Alright, so now we're going to move on to the next chapter, which is equilibrium. So what is chemical equilibrium? Well, it is the state where the concentrations of all reactants and products remain the same over time. Now that doesn't mean that the concentration of the products is equal to the concentration of the reactants. It just means that they remain the same. Now, most reactions can proceed in the forward directions as well as the reverse direction, but the reaction tends to favor one side or the other. Either the majority of the reaction, so that we're going to have a higher concentration of products than reactants, or a higher concentration of reactants than products. Now, how does this relate to kinetics? Well, the reactants are going to react at a specific rate, or the kinetics, that go to products. And the same thing in the reverse. The products are going to react at a specific rate going back into reactants. And the study of that is going to determine what our equilibrium and where our equilibrium will lie. Is it going to favor the products or is it going to favor the reactants? And once again, the equilibrium is when the forward rate, so that's our change of concentration over time, is equal to our reverse rate, meaning they're going back and forth at the same time. Now the concentrations are not necessarily the same, but the rate at which they are changing is the same. So when we look at an equilibrium reaction, first thing we want to ask ourselves is, which way does the equilibrium lie? Meaning, are we going to form more reactant or are we going to form more product? Now if we're going to form more product, then it is going to lie to the right. So here, the right means we form more product. Then if it lies to the left, that means we're going to form more reactant. Now, it could also be somewhere in between. It could be just barely favoring the product or just barely favoring that reactant. So what is going to help us to determine that? Or what are the conditions of our reaction? Is it going to be done at a cold temperature, at a high temperature, under high pressure, low pressure? The first thing we want to look at are the initial concentrations. Are we going to start out with a very high concentration of product? Because that means we're probably going to favor reactants, because everything is going to collide more often. Because remember, it's those collisions that lead to a reaction. We have to have the two actual molecules coming together to form that collision. Then it also depends on the energies of those reactants and products. Are we at a high temperature where there's lots of energies? Because remember, the more temperature we have, because our temperature is a direct measurement of our kinetic energy, which is movement, are we going to have a lot more collisions because we have a higher energy in those reactants? Or look at the energy of our products. If we have a lot more energy in our products, that means we can go back over that bump, back over that big activation energy, if it's an exothermic reaction, and form reactants again. Then also the degrees of organization. Now, if we think about solids, liquids, and gases, which one of those is the most organized? Well, the solid, of course, because our solid is going to form a crystal structure. Whereas those molecules, they're vibrating, but they're not moving around, so they are very organized. Now our liquids, those molecules are still interacting with each other. They're moving, but they're also able to slide around. They can move a lot more freely than in a solid. And finally, our gases, that's the most unorganized form. Those gas molecules can move around freely, and we assume that they do not interact with each other. And that is when we have the most types of reactions, because we have the most energy. Now this is the last bit of information for this video, and it's just a very light introduction into the equilibrium constant. So this is good to understand, where do we come up with the equilibrium constant. So for this, we have our basic reaction. A plus B gives C and D, where the lowercase letters represent the coefficients, the large letters represent the molecule, or the reactant and product. So our K is just basically, if we look at this, it is products over reactants. So we have the concentration, that's what the brackets mean, the concentration of C raised to the coefficient times the concentration of D raised to the coefficient divided by concentration of A raised to the coefficient and B raised to the coefficient. Now temperature has a very large effect on our equilibrium, because that also depends on what type of reaction. Is it exothermic? Is it an endothermic? So our temperature, just like when our temperature is going to affect the rate of a reaction, it's going to therefore affect the rate at which our products go to reactants and reactants go to products. In our K, because we have concentration over a concentration, it is without units. So you guys can do these problems and not have to worry about, did I get the correct units? Such as with our K in the previous chapter, you had to have the correct units for the constant K. Now there are no units for this capital K. Now our K, that capital K, at the same temperature, will always be the same. Meaning if we have a reaction that, say, started out with 1 molar A, we're always going to form the exact same concentration of C and D, whereas if we started with half a molar, 0.5 molar of A, we're going to form the same ratio of C and D. So our K will always be the same, no matter how much our initial concentration of A and B. The equilibrium, the capital letter K, will be the same.